Hey, what's up? AP Calculus. Today we're looking at 5.2 mean value theorem. This is part 1. We're going to spend the next time doing part 2. So what the mean value theorem says is that if f is continuous on this closed interval AB and differentiable at every point, then there must be at least one point where the average rate of change is equal to the instantaneous rate of change. So what that looks like in formula form is this, right? This is the instantaneous. F prime of C, right? That would be the tangent line. And then this is the average, which is the secant line. So what it looks like then, so we're looking at this function f from A to B, right? So if we draw a line connecting A to B, that would represent the average slope. So what they're saying is at some point on this graph, there's got to be a tangent line with that same slope. We don't know how many times, but we know definitely at least one time we're going to have the same slope. Okay, so again, it's got to meet these three criteria to begin with, right? So it's got to be continuous, it's got to be on a closed interval, and it's got to be differentiable over that interval. Okay? Let's get into some examples. So if we're looking at f of x equals x squared, so we know exactly what x squared looks like, right? It's a parabola. The vertex is at the origin. So we're trying to see what happens to this parabola from 0 to 2. So over this interval. Right, we're trying to find how the mean value theorem applies to this one thing. So what we're going to do is we're going to find the derivative. So we have 2x, right? And we know that the average slope, so this would be the average slope. I mean, that would be the instantaneous. And the average rate of change from 0 to 2, what we're going to do is we're going to do f of 2 minus f of 0 over 2 minus 0. So the value at 2 is going to be 2 squared 4 minus 0 squared, which is 0, over 2 is equal to 2. And now we're trying to find on our instantaneous rate of change, where is it going to be equal to 2? So if we divide here, we see that, let's clean that up. When x equals 1, then we should have slope 2. Okay, so again, we use this form, right? So here's where we found our average, which was 2. That's this part. Our instantaneous, we did the derivative. So this is the secant, or the average. This one represents the instantaneous, and we're trying to find at where does the mean value theorem apply. And we just did our algebra and saw that x is equal to 1. Okay. Now in the next example, it says explain why the functions fail the mean value theorem on the interval -1 to 1. Okay, so first of all, we know that the interval is not going to be the reason, right? Because the interval checks out. The interval is closed. It's got brackets on both ends. Now, for f of x equals square root x squared plus 1, this is just a fancy way of doing absolute value. So this looks like an absolute value graph lifted up 1. So it usually starts or has its vertex at the origin. In this case, it's up 1. But it looks the same, right? It's V-shaped. So notice here, well, let's go back to the previous page. So we know the interval's checked out, right? So either it's not differentiable or it's not continuous would be reasons why it would fail mean value theorem. So we definitely know this is continuous, so that part checks out. Now, that must mean that it's not differentiable. At some point. Now let's look at this line. An absolute value example is pretty easy to see, right? Because we know it's differentiable across all these straight parts for sure, right? There's no gaps in there, there's no weird stuff. But what we have here is a corner. There's a corner where x is equal to 0. So sometimes if you have to graph it out, then you might want to graph it out. Otherwise, if we know just by looking at it that this is an absolute value graph, then we know that there's going to be a corner someplace in this interval. Now keep in mind, if we were talking about an interval outside the corner, then the corner wouldn't make a difference and it should be, then mean value theorem should apply. Okay, part B. Same thing, we know that the interval is okay, so we're checking to see if it's not differentiable or if it's not continuous. So let's go ahead and check continuity first then for this one. Let's change colors here. So we're mostly concerned, or we're only concerned with continuity for this one because we know that this is a polynomial function and continuous, and so is the bottom one. Over the interval, we just need to check where x is equal to 1 because that's the place where they meet up. So there could be a discontinuity there. So what we're going to do is we're going to plug in 1. So that's going to be equal to 1 plus 3, which is 4. And then we're going to do the same thing for the second part of our function, 1 squared plus 1, which is 2. So notice that these don't match up. Therefore, this is not continuous. At x equals 1. Okay, so we just explained why these functions fail to meet MVT. And again, the 3 criteria for MVT to be applicable is that it needs to be continuous, it needs to have a closed interval, and it needs to be differentiable over that interval. Okay, next. This time they're giving us function f of x equals square root 1 minus x squared. So what this looks like if we graphed it is like a semicircle. And that they're saying that a is at -1, 0. And b is at 1, 0. Okay, so it says find the tangent equal to the secant AB. Well, the secant of AB is pretty easy. That's going to be slope 0. Secant AB is equal to 0, right? If we wanted to, we could plug in the points into the y2 minus y1 over x2 minus x1 thing, or even use the one that they gave us, right? F of b minus f of a over b minus a. All of these things will get us to 0. All right, so what they're asking us to do is find when the tangent is equal to the secant AB. So let's take this. Let's rewrite it in rational exponent form so that we can do power rule. So we're going to do f prime of x then is going to be equal to 1/2 1 minus x squared to the negative 1/2. We have to remember the chain. I forgot to do that in last lesson, right? So our chain in here, 1 derives out, but then we have negative x squared, so that's negative 2x, right? The derivative of negative x squared is negative 2x. And let's clean this up. So the 2 is going to cancel out. We have 1 over, we still have this negative sign, and then we're going to have 1 minus x squared in the bottom, and we're going to take the square root of that. Oops, we also have our x on top, so let's, can't forget our x, so we have our x on top. Okay, so let's go ahead and figure this out. When is this going to be equal to 0? Well, we know that we don't have to mess with the bottom, right? The bottom is not going to make us have a 0. In fact, if we multiplied by the bottom the square root of 1 minus x squared on both sides, it'd cancel the left-hand side, so we'd have just x, and then 0 times anything is 0. So just more reinforcement that we're just looking for when the top is equal to 0. Right, so it says x equal to 0. We don't even have to do any algebra because it's just an x up there. So if you notice, let's go ahead and reinforce that. So 0 is located halfway between 1 and negative 1. Right, so up here on our graph, you notice that that would definitely be where our slope is equal to 0. We'd have a horizontal tangent at that point. So just verifying graphically what we just saw, what we just did using our calculus. Okay, and then the last one probably is the most relevant and it makes the most sense. So in this situation, we have a car, we're accelerating from 0, right? So we're at a standstill. And then we go to some point. The time is 8 seconds, right? So this takes 8 seconds. And we traveled 352 feet. So we did 352 feet in 8 seconds. And then I guess we can divide that. So 352 divided by 8. Let me get a calculator. Is 44 feet per second. And this is our average, right? So the thing that it's asking us is what can be said using MVT. So at some point, we must, or the car must have been, going 44 feet per second. Now we could change that to miles per hour. Let's do that, just because I'm curious. So there's 3,600 seconds per hour. And then there's going to be 5,280. Yeah, that sounds right. 5,280 feet per mile, right? So then we can check feet and feet cancel, seconds and seconds cancel, so we're left in miles per hour. Good. So we're going to do 3600 times 44 divided by 5280. So we're going about 60 miles per hour on average. Does that seem right? Alright, well, I can't find the answer in miles per hour, so sounds about right, so we'll roll with it. Oh no, I did that wrong. 352 divided by 8, 440. Did I put the things in the wrong place? 44 times 3600. Oh, I wrote the thing wrong. 158400 divided by 5280. There we go. Is 30 miles per hour. Okay, so that just means that at some point we know that we're going exactly 30 miles per hour because the average rate was 30 miles per hour. Okay, that's it for today. Good job.